Okay, let's dive into this. If you've ever stopped to wonder how simply tapping on your screen instantly summons a web page from a server literally thousands of miles away, well, you're in the right place. In today's Explainer, we're unpacking the absolute core of our digital world, network architecture and the TCP/IP model. We're going to break down the deeply complex, almost magical infrastructure of the internet into four really digestible, stacking layers that make literally all modern communication possible. Now, to really grasp how data moves, it helps to visualize the whole system. Think of the internet's protocol stack like a giant, multi-story packet factory. The lower levels down in the basement, they handle all the heavy lifting, all the gritty physical details like electrical signals and raw hardware. They do this so that the upper levels, where your favorite apps actually live, just don't have to worry about any of it. It's a brilliantly designed system built entirely on abstraction and delegation. Here is our roadmap for today. We're looking at Layer 1, the link layer, Layer 2, the Internetwork Layer, Layer 3, the transport layer, Layer 4, the application layer, and finally, stacking it all together. So we're going to trace the exact path your data travels as it moves through this TCP/IP stack. It's essentially an incredibly fast relay race of information, starting right at the physical hardware level and seamlessly passing the baton all the way up to your user-facing software. Layer 1, the link layer. All right, starting at the absolute foundation. At its core, the link layer really just has one primary job, getting a packet of data across one single physical connection. Network engineers actually call this a hop. And by isolating this one specific task at the very bottom, the link layer shields all those upper layers from having to deal with specific hardware quirks. I mean, the upper layers do not care if your data is traveling over a Wi-Fi radio wave or a literal pulse of light in a glass tube. The link layer handles all that translation natively. And what's super interesting here is the stark contrast in the types of environments this layer has to manage. On one hand, you've got shared connections. Think about the Wi-Fi at a crowded coffee shop. Because the airwaves are shared by every single phone and laptop in the room, the link layer requires incredibly strict traffic rules to ensure fair access and avoid data collisions. But on the other hand, you have non-shared connections. These are things like the dedicated private fiber optic lines sitting between massive core internet routers. They don't share airspace with anyone, so they can just blast data at mind-blowing speeds. Layer 2, the Internetwork Layer. So, moving up a floor, once your data successfully makes that first local hop, the Internet Protocol, or IP, takes the wheel. The IP layer uses these unique, globally recognized IP addresses to dynamically route your packets across multiple hops. It's this chaotic, vast system that somehow navigates from billions of possible sources to billions of destinations, and it doesn't pre-plan the whole trip. Actually, it dynamically adjusts on the fly based on network traffic or sudden outages, constantly figuring out the best path to your target. There's this vivid analogy from the source material that I absolutely love. Think of IP routers like highly efficient escorts working at a bustling, crazy train station. When a packet arrives at a router, that router instantly checks the packet's destination IP address and boom, immediately points it down the correct outbound track. If you were the packet, you'd never have to stare at a map or check a departure screen. The routers handle all the insanely complex navigation for you, hop by hop, until you arrive. But here is the critical catch. While the IP layer is incredibly fast and super adaptable, it is absolutely not 100% reliable. Sometimes networks just get congested, and routers literally have to drop packets in the trash. Which obviously leads us to a pretty important question. What exactly happens when parts of your message inevitably go missing, get dropped, or show up totally out of order? Layer 3, the transport layer. Enter the third floor. When that messy stream of data reaches its destination, the transport layer, specifically TCP, steps in to save the day. It buffers all those incoming packets because, remember, they probably took totally different routes across the globe and arrived completely scrambled. TCP patiently sorts them out, reassembling them in the correct order, snapping the packets together perfectly like puzzle pieces. It completely compensates for the wild unpredictability of the IP layer sitting right below it. TCP is honestly the unsung hero here because it ensures total reliability. If a packet gets lost, TCP notices right away and tells the sender, hey, send that one again. But arguably, its most fascinating feature is that TCP is uniquely polite. It constantly monitors the speed and congestion of the network. If it senses the internet is struggling, TCP dynamically shrinks its own transmission window. It literally slows down the flow of data so it doesn't clog the pipes for everyone else. That polite flow control is literally what keeps the entire global internet stable. Layer 4, the application layer. Finally, we reach the penthouse. You're definitely familiar with these acronyms. These protocols take that abstract, highly mathematical network stack and finally connect it to the actual software tools we use every single day. HTTP is powering the web browser you are probably using to watch this explainer right now. SMTP handles your emails. DNS is what translates clunky human web addresses into those raw IP addresses the lower layers need. Up here, it is all about the user experience. At this top layer, your client applications are basically using the services of the floors below to dial up and establish connections to specific ports on destination servers. You can think of a web server as an application that's just always running, always listening on a very specific port, just sitting there waiting for a browser to knock on its door and ask for a web page.
Stacking it all together.
Okay, bringing it all home. This right here is the true genius of the TCP/IP model, encapsulation. As your data moves down your computer stack to be sent out into the world, each layer wraps that data in its own specific header. The application layer hands off the data. The transport layer slaps on a TCP header with port numbers. The Internetwork layer wraps all of that in an IP header with destination addresses. And finally, the link layer seals it with a hardware address. It is exactly like putting a letter in an envelope, putting that envelope in a box, and putting that box in a massive shipping crate. When the data finally reaches its destination, it travels up the receiver stack, and each layer strips off its respective header one by one until the pure original data is handed to the software. You know, when you really step back and look at it, the internet is just this massive, decentralized network of billions of independent computers. There's no central boss, there's no master server running the show. The fact that any of this works at all relies completely on this open architecture and those polite protocols like TCP that just inherently agree to share resources fairly. It is a wonderfully fragile, yet absolute triumph of human engineering. Hopefully this gave you a deeper appreciation for the invisible magic happening right behind your screen. So as we wrap up this explainer, I'll leave you with this to chew on. How incredible is it that a system of billions of independent computers cooperates seamlessly every single second of the day, relying on nothing more than polite protocols?